We spend so much time talking about these incredibly powerful AI models, right? Their size, their speed, what they can do.
Absolutely. The focus is often on the model itself.
But here's the thing, the real secret sauce, the foundation for all that AI magic, it's almost always the data they learn from.
He really is.
And what if getting that data, the right data, is incredibly difficult, maybe super expensive, and often, honestly, just opaque? You don't know what's in there.
That's a huge problem in the field.
Well, today you're joining us for a deep dive into something we think is potentially a game changer for AI data, Essential Web v1.0.
Mm-hmm.
Now, this isn't just another big beta dump. It's massive, yes, but it's also precisely organized, a collection of web data that could really shift how we train the next generation of LLMs.
It's quite an ambition.
So our mission today, to explore how this new dataset, which comes out of a recent paper from Essential AI, tackles some major hurdles in data curation, making it faster, cheaper, and way more transparent.
And there's some surprising details in how they did it.
Definitely. We're digging into their paper, Essential Web v1.0, 24T tokens of organized web data, to pull out the key insights for you.
It's so true what you said about data being fundamental. It's not just important, it's everything for how these models pick up skills and knowledge.
Right. Garbage in, garbage out, essentially.
Exactly. Without the right data, they just can't learn effectively. And that leads us straight into this major bottleneck we see in AI development right now.
Okay, so what are the big issues?
Well, there are a few, and they really stack up. First, there's just a lack of massive, well-organized data sets that are actually open and available for pre-training.
Okay.
A lot of the pipelines used to create data are kept private. They cost a fortune. They're just not easy to access.
So it locks people out.
It does.
Mm-hmm.
And then, even with open-weight models, you often don't get the full picture of what data they were trained on. That makes it incredibly hard to reproduce research or, even audit what these models have actually learned.
Which seems pretty important.
Crucial. And if you look at the open source data sets that are out there, they tend to be one of two things. Either these enormous general collections sorted by quality scores you can't really interpret.
So you don't know why something is high quality.
Exactly. Or you get much smaller, very niche data sets built with these custom complex pipelines that are, again, hard to replicate.
And I was struck by the fact that both types, the giant messy ones and the small custom ones, they're usually unstructured, right? Hard to explore, hard to build on.
Very much so. And just making them, even in their raw state, takes a huge amount of computing power.
Yeah, the analogy I was thinking of is imagine trying to cook a gourmet meal. But your options are either getting ingredients dumped into this giant, disorganized warehouse with no labels.
Right.
Or you have these tiny, super specific pantries, but each one was built by a different chef using secret methods they won't share.
That's a great analogy. It's chaos if you're trying to actually build something new consistently.
So how does Essential Web v1.0 start to fix this? Where does it fit in?
Well, the core idea is scale plus organization. It's a huge data set, 24 trillion tokens taken from Common Crawl.
Okay, Common Crawl, that's the big public web scrape, right?
Exactly. Massive, but famously messy. The key difference here, the absolute game changer, is that every single document in Essential Web v1.0 gets annotated.
Annotated how?
The detailed 12-category taxonomy. It covers the document's topic, its format, how complex the content is, and its quality.
12 categories for every document. Wow.
Yeah, and this is what flips the script. Because now, researchers or practitioners can create new data sets really quickly and cheaply. They just write simple SQL-like filters using this metadata.
Okay, so instead of wrestling with raw data, it's more like querying a database.
Precisely. Think less complex data engineering, more like using a superpowered search engine. You can essentially say, give me all the chemistry documents, but only the highly technical ones for, say, grad students, and filter out the ads and product pages.
And it just pulls them.
It pulls exactly what you asked for, like running a detailed database query.
Okay, that example they gave in the paper really drove it home for me, the chemistry one.
Oh yeah, that's a good one.
So today, a researcher needs chemistry data. They first have to train a model just to find chemistry documents, which is hard itself.
Right, finding niche labeled data is tough.
Then run it across maybe hundreds of millions of web pages. The paper says this can take weeks, even months.
Easily. It's a huge undertaking.
But with Essential Web v1.0, they just filter for chemistry, filter out low quality, maybe filter for reasoning dense, and the query takes, what, less than 15 minutes to write?
That's what they claim. It cuts curation time from potentially months down to just hours or days.
That's not just faster, that feels transformative. It lowers the bar, right?
Yeah.
Smaller labs, maybe even individuals could potentially do this kind of curation.
Absolutely. It could really democratize access to high-quality, tailored data. Imagine the innovation that could spark.
So the magic is really in this taxonomy, this labeling system.
It really is.
Yeah.
And it's quite thoughtfully designed. These 12 categories fall into 5 main groups.
Okay, break it down for us.
So for topic, they use something called free decimal correspondence, FDC. Think of it like a public version of the Dewey Decimal System libraries use.
Oh, okay. Familiar.
Yeah, and it's hierarchical, level 1, broad, like science. Level 2 gets finer, like mathematics. Level 3, very fine, like algebra.
Got it.
Then there's content complexity. Here they bring in Bloom's taxonomy, that framework from education about cognitive skills.
Right, like recall versus analysis versus creation.
Exactly. So they label based on the thinking required cognitive process, knowledge domain, and also things like reasoning depth and education level.
Interesting. So you can filter for stuff that requires deep reasoning.
Precisely. They also categorize web page type. Is it an article, a forum post, etc.?
Right.
Document quality, like technical correctness. And even extraction issues. Did text get mangled during processing? Things like that.
That seems incredibly detailed.
It is, and it ties into what they call the 5 desiderata, the essential requirements for a good web-scale taxonomy.
Okay, what are those?
First, orthogonality. Each category should give independent information, not overlap too much.
Makes sense.
Second, expressivity. It needs to be detailed enough so you can actually combine labels to find very specific subsets of data.
Like our chemistry example.
Exactly. Third, correctness. The labels need to be assigned consistently. Fourth, efficiency. The classifier applying these labels has to be fast, given the scale we're talking about.
24 trillion tokens. Yeah, speed matters.
Immensely. And finally, effectiveness. Does it actually work? Does using this taxonomy lead to better models downstream? That's the ultimate test.
And was it expressive enough?
Well, get this. Across the 23.6 billion documents they processed, they found 14.1 million unique combinations of just the primary labels and 1.2 billion unique combinations if you include secondary labels.
Whoa, that's a lot of unique combinations.
It really paints a picture of a very fine-grained coordinate system for navigating web data.
Okay, so we've got this powerful labeling system, but the scale is still just staggering 24 trillion tokens. How on earth do they actually do the labeling? How did Essential AI manage that efficiently?
Right, that's the engineering challenge. They used a pretty clever 5-stage approach. Develop the taxonomy, select a teacher model, distill it to a student model, run inference at scale, and then check the downstream performance.
Teacher model, student model. Explain that.
Okay, so the initial labeling, they use powerful, large, open-weight LLMs. Think models like Qwen 2.532b Instruct. These were the teachers.
The smart ones.
Very smart, capable of understanding the nuances needed for the 12-category taxonomy. They essentially acted as expert human annotators, but automated.
But presumably slow and expensive to run on billions of documents.
Exactly. That's where the student model comes in. They train a much, much smaller model, EAI to still 0.5b, only 500 million parameters.
Hey, tiny compared to the teacher.
Tiny. And they use this technique called distillation. Basically, you fine-tune the smaller student model using the high-quality labels generated by the bigger teacher model. The student learns to mimic the teacher's labeling ability.
Ah, so it learns the task, but in a much more compact, efficient form.
Precisely. The student model can then do the labeling much, much faster and cheaper.
And the numbers on that efficiency are pretty wild, right?
They are. So, labeling all 23.6 billion documents, the 24 trillion tokens. The student model did that in about 90,000 AMD MI300X GPU hours.
Okay. Put that in context.
That's roughly 1 week of compute time if you're running on 512 of those high-end AMD GPUs.
Wow. Okay, so still a massive compute job, but feasible.
Feasible, yeah. But they needed serious optimization to get there. And what's really amazing is how much faster the student was compared to the teacher.
How did they speed it up so much?
They pulled 3 main levers, as they put it. First, obviously making the model much smaller, 0.5 billion parameters instead of 32 billion. Second, they drastically shortened the required output length. The teacher model might output, say, 791 tokens on average to explain its labeling. They trained the student to output just the essential labels, averaging only 51 tokens.
Huge difference.
Massive. And third, they use something called context distillation. This basically removes the need to feed the full prompt back into the model during fine-tuning, saving computation.
And the result of all that.
An incredible 50 times faster inference speed for the student model compared to the teacher model it learned from.
50 times. Okay, but the big question then is quality. Did they sacrifice accuracy for speed?
That's always the concern with distillation. But they checked this carefully. The student model, EAI distilled to 0.5b, had minimal quality loss.
How minimal?
Its agreement with the teacher model, measured by something called a kappa score, which checks agreement beyond chance, was within 3% of the teacher's own consistency.
That's pretty close.
Very close. And they also checked if the different label categories were becoming redundant. Using a measure called NMI, they found it stayed below 0.10, which is very low, meaning each category was still providing independent information. Quality largely maintained, speed massively increased.
Okay, so careful organization, clever engineering, impressive speed, maintained quality. What does this mean for actually training models? Does this data lead to better AI?
That's the payoff, right? The
Yeah.
effectiveness part. And the results here are really compelling.
What did they find?
They found that using simple filters based on this taxonomy, just querying the metadata on Essential Web v1.0 without needing any extra domain-specific training data or complex pipelines, produced datasets that performed really well.
How well?
Highly competitive with, and in several cases, significantly better than, existing state-of-the-art datasets for specific domains.
Whoa, wait. So just using the general taxonomy labels beats specialized datasets?
In some key areas, yes. For web code, models trained on data filtered from Essential Web outperformed the previous best by 14.3%.
Okay, that's significant.
For STEM field science, tech, engineering, math, the improvement was even bigger, 24.5% better than state-of-the-art.
Wow.
For medical data, an 8.6% improvement. And for math, it was competitive within 8% of the best, but, and this is key, achieved with vastly simpler curation. No bespoke pipeline needed.
That feels like the really revolutionary part. One organized data set, simple filters, and you get state-of-the-art performance across different domains.
It really challenges the idea that you absolutely need a separate, complex, expensive pipeline for every single domain you care about. This suggests a more general approach might be possible and maybe even better.
And how does it manage to find the right stuff so well? You mentioned domain recall earlier.
Yeah, that's a measure of how much of the relevant stuff you actually capture. Their examples are great. If you filter for the FTC code 51 mathematics,
Okay.
the system finds 98% of pages that experts verified as being about math, while only keeping 0.5% of the entire 24T token dataset.
So it's incredibly precise.
Yeah.
Very little noise.
Extremely precise. Minimal waste. Same for web code filter for the right labels, and you get 96.5% of the good code pages while only keeping 7.5% of the total web data. That's super efficient compared to older methods.
This really does change the game then. Data curation goes from being this complex, opaque, expensive thing
To being much more like a search problem. Yeah. Something potentially anyone with the right query skills could tackle.
You know, I always had this image of data curation as this huge hidden operation inside big labs. This paper kind of blows that up.
That's clearly the hope behind it. They talk about wanting Essential Web v1.0 to become a community commons.
A public resource.
Exactly. A shared resource that others can use to build on, to audit, to refine, maybe find new ways to curate data. The idea is to accelerate open research on training data, which, let's face it, is often the most valuable part of building an LLM, but also the least shared.
Could this kind of thing genuinely democratize AI development, start to level the playing field a bit?
That's the big question, isn't it? It certainly feels like a step in that direction. Providing this kind of interpretable structure, this coordinate system, on top of the messy web, it brings order.
It makes it navigable.
Exactly. It makes the chaos navigable.
And crucially, for transparency and letting people try this, they've made it available, right?
They have. Both the Essential Web v1.0 dataset annotations and that efficient little student model, EAI distilled 0.5b, are up on HuggingFace.
So people can actually download it, poke around, run their own queries.
Yep. See how it works, experiment with it. Full transparency there.
So recapping, we've seen how meticulously organizing and labeling web data at massive scale can make AI training, well, more efficient, definitely more accessible, and potentially lead to models that perform better across a range of different areas.
It's a really powerful demonstration of the value of structured data.
Definitely feels like a significant step, potentially changing who gets to build powerful AI and how.
But the creators themselves pose an interesting final thought. They acknowledge that while taxonomies like this are a fantastic tool right now, It's still an open question. Will these kinds of structured labeled datasets remain central to building the best AI models? Or are they maybe just a stepping stone, a bridge towards fully unsupervised methods where the AI figures out the structure entirely on its own?
Hmm, that's fascinating. So after this deep dive into making data organized and searchable, what does that suggest to you, our listener, about how AI might learn in the future? Is structure the key or just a temporary scaffold? Something to think about.